Welcome everybody to our Gamma seminar. Today we have the pleasure to guest Casey Blaker from Augusta University, who is going to talk about curvature and holonomy in double Lie groupoids. So Casey, thank you very much for accepting our invitation. It's a pleasure to have you here, and the floor is yours.
Wonderful. First of all, thank you to Javier for the invitation to speak, and thank you to everyone in the audience for being here. So as mentioned, I will discuss curvature and holonomy in double Lie groupoids. I should say at the very outset that this has been joint work in progress with Dr. Derek Krepski at the University of Manitoba in Winnipeg. We have a couple of sort of long-running projects, and this is one of them. So the plan for the talk is as follows. First, I will review the classical Ambrose-Singer theorem in the setting of principal bundles. Then I will introduce Lie groupoids and Lie algebroids, as well as connections, curvature, and holonomy on them, as well as Kirill Mackenzie's extension of the Ambrose-Singer theorem to that setting. Then I will introduce double Lie groupoids and LA-groupoids to set the stage for a heavily differential geometric higher Ambrose-Singer theorem, which is the most speculative section at the very end. And so that is the material some of the material that I've been thinking about recently. All right. Let's start with the classical Ambrose-Singer theorem. We'll just recall some basic constructions from differential geometry. First, we have the notion of a connection, which we'll take heuristically as being an identification of infinitesimally near fibers of a bundle. This gives us a method of parallel transport, which is then the integration of those infinitesimal fiber identifications. Given a path on the base space M, this yields a fiber isomorphism from the beginning of the path to the fiber at the end of the path, given by composing those infinitesimal isomorphisms.
No, sure.
Oh, yes?
Nothing.
Oh, okay. So this gives us our construction of holonomy, which is given as follows. We fix a particular fiber, say that above X in this image, and we consider all of the fiber automorphisms induced by parallel transport along loops based at X. This gives us a Lie group, hol X, or a Lie subgroup of the automorphism group of our fiber. So curvature now, so that's the global view. Now looking at the infinitesimal side, we can think of curvature as being the infinitesimal rate of change of a connection with respect to itself. A connection gives us it enables us to take derivatives, to take infinitesimal rates of change, and so we can simply apply that to itself. So in this image, we want to compare the parallel transports along these dark blue paths. So we have a family of paths. The family is parameterized by S. The paths themselves are parameterized by T. This instantaneous rate of change will then involve taking both S and T to 0. This is equivalent to taking the parallel transport along this light blue path, QTS. We can think very informally of curvature as being kind of like a parallel transport or a holonomy density. this idea is, okay, so we see that we're in the setting of something that looks very similar to the Stokes type theorems, where we can create a mesh grid. These little blue squares, they have side length, say h. We're going to take those to 0. We can take the parallel transport along all of them and sum them up. We get internal cancellation so that so that we're left on this right-hand side here with the parallel transport along the loop, which is the holonomy. And then on the left-hand side here, we are in some sense then integrating the differential of the connection over the interior. So that's like the curvature, excuse me, curvature. This intuition is formalized in the Ambrose-Singer theorem of 1953, which states that indeed, yes, curvature generates holonomy. The setting there is that we have a G principal bundle, but we don't need to go into that formalism actually. We just pick a particular fiber, say that above X. We look at the Lie group of fiber automorphisms given by parallel transport. That is a Lie subgroup, so that's our group G. That's our group Hall U, where U is an initial fixed point that we're parallel transporting around. And then Ambrose-Singer says that the Lie algebra to that Lie group is given by applying the curvature in P to all pairs of vectors tangent to any tangent to the holonomy bundle. That is the bundle given by all possible parallel transports of U over M. So this is the notion. So that this generates the Lie algebra of the holonomy group is the notion in which curvature generates holonomy for Ambrose-Singer. So this is the starting point. That's the background. Okay, now I will introduce Lie groupoids and Lie algebroids, and then discuss Mackenzie's extension of the Ambrose-Singer theorem to groupoid and algebroid connections and holonomy. Okay, so as our first definition then, a Lie groupoid consists of two manifolds, G and M. We think of G, which is green down here, as a manifold of arrows, so it's our space of arrows. M, which is black here, is, well, we could say a space of objects or just a space of points. So the idea is that we're in a setting where we can compose, where we want to compose arrows, take their inverses, have unit arrows over this base space M. That is encoded in this second data class of data that we have, which are these smooth maps from G to M. So from the space of arrows to the space of points, we have a target map returning the tip of an arrow, the source map returning the base. To each point of M, like this X here, we have a distinguished unit arrow, which has source and target that point. And we have a and then we have a composition map, which takes which will take a pair of arrows that the target of which is the source of the other to a composed arrow. So this data is subject to two kinds of conditions. First, they are subject to algebraic conditions, which is a collection of group-like conditions. So we need associativity of composition. We want existence of inverses, and the units should should indeed be units with respect to the composition map. Second, we have smooth conditions, which for us will, I think, here simply be that we want all maps to be smooth and the source and the targets to be surjective submersions. Okay, so there's a special map chi from the space of arrows to the square of the base, to ordered pairs on the base, called the anchor map, which simply assigns to each arrow its source and its target together. When this anchor map is surjective, we say that the Lie-groupoid is transitive. In other words, that means that for every pair of points on the base, there exists an arrow G connecting those 2 points. And we use this notation, G sub X sub Y, to be the collection of arrows from X to Y. We can next define the adjoint group, also called the vertex group, at any point X, which is just the collection of all arrows at X that the source and targets of which are X. So it's all arrows from the point to itself. It can be shown that this is this is actually a Lie group. The identity of that Lie group is the unit arrow at X. Okay, so that is the global construction. We can differentiate that to get the construction of a Lie algebroid, which stands in relation to Lie groupoid as a Lie algebra stands in relation to a Lie group. So a Lie algebroid comprises a vector bundle A over M, a Lie bracket on sections of A, and the data of an anchor map, which is a map from A to the tangent bundle of M. So here is I have depicted this data. We can see that so the anchor map, in some sense, the anchor map realizes the elements of A as tangent vectors. This data is subject to the following technical looking condition. My interpretation of this condition is that, well, I think maybe for me the easiest way of reading it is that the map bracket A is a differential operator on sections of the Lie algebroid.
It is said that this is a Leibniz-like condition, yeah?
Yes, yeah, exactly. Yeah, so yeah. So row A is like A acting as in its vector field part. Yeah. And then this would just be the multiplication rule, the
yeah, and I don't know if you're gonna tell, but the anchor map by means of the Leibniz-like conditions, these conditions you have in here allow you to say that the anchor map is a vector bundlemorphism. Yeah, sometimes it's added like a part of the definitions in some old works, and others they say that it's a it can be proved that it is a consequence of these properties.
Oh, interesting. Yeah, interesting. Well, so we say that the anchor map, I'm sorry, we say that the Leibniz algebroid, I'm sorry, that the Lie algebroid is transitive when the anchor map is surjective. We'll see later on that the anchor map is kind of like an infinitesimal target map. So those two notions of, so these two notions of transitivity locally coincide. We can then define the adjoint algebra of the Lie algebroid at X to be the kernel of the anchor map. So it's those elements which act as the zero tangent vector at X. And it can be shown that that in fact this is a Lie algebra. We then so I don't say so here, but we then obtain actually in both the Lie groupoid case and the Lie algebroid case a bundle of an adjoint bundle of Lie groups and Lie algebras respectively. Okay, so given a Lie groupoid G over M, we can differentiate it to obtain a Lie algebroid A over M in the following rather straightforward way. The vector bundle is given as simply the kernel of the derivative of the source map along the unit embedding of M into the space of arrows. So we identify M with its embedding as the unit arrows in G, and heuristically then we can think of the Lie algebroid elements as being like fixed source infinitesimally small arrows. So they are going to be tangent to a path of arrows where the path starts with tip and tail at X, and then the tail might be extending, but the tip has to stay fixed. The anchor map, as I had mentioned on an earlier slide, is then the differential of the target map. And when we wish to indicate this relation, we might write the algebroid as AG, or algebroid of the groupoid G. Okay, so now I want to very briefly run through a few examples, canonical simple examples, that of Lie group, Lie algebra, Lie group bundle, Lie algebra bundle, pair groupoid, trivial groupoid, and a Tia groupoid, as well as their algebroids. As the most trivial example of a Lie groupoid, when the base space is simply a point, we can take the Lie groupoid to be any Lie group. We can take any Lie group over that point, realized as a space of arrows. The associated Lie algebroid is the Lie algebra G, or fract G, of the Lie group G. The anchor map is, of course, 0. This, as somewhat less trivial, we can extend that to looking at a Lie group bundle, the associated Lie algebra, the associated Lie algebroid of which is the bundle of Lie algebras of the fibers of G. A somewhat more interesting example would be the pair groupoid and its tangent algebroid. So the pair groupoid is defined in the following way: to each points x and y of M, we associate a unique arrow. So the space of arrows is simply M squared, or M2. The tangent algebroid, or the infinitesimal version of this, is then the tangent algebroid, which as a vector bundle is the tangent space to M, and the Lie algebroid bracket is the bracket on vector fields. So the anchor map is just the identity in this case. The trivial groupoid with fixed structure group H associates to each point x and y of M an H worth of arrows. So arrows from x to y consist of the points x and y and parameterized by the points x and y and an element of H. Composition is then given by group multiplication. We can its infinitesimal counterpart is the trivial algebroid with structurally algebra fractor H, which consists of sums of vector, the sections of which consist of sums of vector fields and H valued functions on M.
Casey,
Yes.
sorry, do you know any physical example where these groupoid and trivial algebroids appear, where you can apply it naturally?
A physical example? No. I don't, unfortunately.
Okay, never mind. Okay.
But the following example, I believe, is much more natural. These are nice toy examples, though, the trivial groupoid.
Yes, to have fun, to see how everything works, and for mathematical stuff they appear. But then if you want to make some physics, some of these they appear, some no. Okay, thank you. Please go on. For sure, Attila will appear, yeah?
Sorry?
Attila group, for sure you will talk about Attila groupoid. Okay, yeah, exactly.
Yes.
That's what
Javier,
was expecting.
maybe I could comment that maybe for me example is if we have a normalized class of differential equations where equivalence group generates equivalence groupoid is the action of groupoid of this group. Yeah, is it true? Yeah, that this is the case. Yeah, so in fact we have trivial groupoid. This means that the groupoid like action groupoid of some group. Yes.
It could well, so actually I don't have as an example the action groupoid. That would have been an excellent example for to have included. I think it's different though, because with the action groupoid, the identity element of the group that's acting would always send a point on the base to itself.
Yes.
So here, though, the identity element of the group that the identity element could be associated to two distinct points. But maybe there's a way of relating this group, the structure group of the trivial groupoid, with some subgroup maybe of a structure group in an action groupoid. I'm not sure.
Okay, thank you.
Okay. And then as our final and inarguably most interesting example, we have the Atiyah groupoid and its infinitesimal Atiyah algebroid. So we start with so here we have an H principal bundle of P over M. The arrows are principal bundle fiber isomorphisms. So they're fiber identifications between potentially distinct fibers. The adjoint bundle of this then comprises of fiber identifications from fibers to themselves, which is just the familiar, or well, relatively familiar adjoint bundle of the underlying principal group. So the Atiyah groupoid is kind of like a generalized adjoint bundle. It's an adjoint bundle where we can identify, where we're also identifying distinct fibers. So the Atiyah algebroid then comprises of, well, we can think of it as infinitesimal fiber identifications, or the identification of a fiber with its infinitesimal neighbor, which we can realize as being H, so structure group invariant vector fields along the fiber. adjoint bundle of this would then be those invariant vector fields which are tangent to the fiber, which is canonically isomorphic to the little adjoint bundle of P. So infinitesimal fiber isomorphisms, or fiber automorphisms. Okay, so in the remainder of this section, I'll define connections, curvatures, curvature, and holonomy on Lie algebroids and Lie groupoids. So first, a Lie algebroid connection, gamma, is nothing but a vector bundle lift of the anchor map. So it sends tangent vectors, and it picks them up. It sends it to some element of A that projects by the anchor map back down to X. It is immediate that such a construction exists precisely when A is transitive. That is precisely when the anchor map is surjective. And maybe a quick comment here, because this was something that had confused me when I first approached this. This is very different from, I think, other notions of connections, because normally when we have a connection realized as a lift, we're lifting to the tangent space of whatever kind of bundle it is. Here, we're sending a tangent vector to elements of the Lie algebroid itself. The curvature of a Lie algebroid connection is then given by this formula, which can be interpreted as being the vertical projection of, as taking two tangent vectors, x and y, extending them to local vector fields on M, x bar and y bar, lifting them by gamma, and then taking the vertical projection in the fiber at X with respect to the with respect to the Lie algebroid bundle gamma. More succinctly, it is the vertical part of the bracket of lifts. It can be shown that a Lie algebroid connection defines a differential operator on the adjoint bundle of A, given by applying sections of the adjoint bundle with the bracket with brackets with respect to lifts of vector fields. And then we here will define the curvature bundle, the resulting curvature bundle, to be the smallest lambda stable subbundle of the adjoint bundle that contains the image of the curvature. So the curvature, so it can be shown that, well, because it is the vertical part of something, the curvature projects down to, by the anchor map, to zero, to the zero vector fields. So we want to take that Lie algebra bundle over M generated by the curvature that is stable under this covariant derivative. Then we'll define the gamma curvature reduction of our Lie algebroid with respect to the Lie algebroid connection as being the curvature bundle in the vertical direction plus the image of the Lie algebroid connection, which gives us a notion of a horizontal bundle over M. It can be shown that that A gamma is a Lie algebroid. We can describe it as the Lie subalgebroid of A generated by the curvature. and containing the connection. All right, so that is that's the infinitesimal side, the Lie algebroid side. Now let's look at the Lie groupoid side. We define a path connection or a system of parallel transport on a Lie groupoid to be a lift from paths PT on M to paths AT in the space of arrows. This assignment gamma, so capital gamma, needs to satisfy smooth and algebraic conditions. So the algebraic conditions are mostly compositional conditions. We can think of, so this is a little bit different from familiar parallel transport. Here, the idea is that as we extend a path on X, we develop a path in the space of arrows above it, the tip of each arrow along that path being at the beginning of our path PT. I'm sorry, the source of the path in the space of arrows being fixed at the start of our path PT, and the tip following along the tip of the path over which the path that we are lifting. It can be shown that we can differentiate path connections on the Lie groupoid G to obtain Lie algebroid connections on AG over M, and in the other direction we can integrate Lie algebroid connections to on the tangent Lie algebroid to obtain path connections on the original Lie groupoid. And then, as a very simple definition, we define the gamma holonomy subgroupoid of G to simply be the image of capital gamma in G. So this is the Lie subgroupoid of all lifted paths, and it can be shown that this is actually a sub Lie groupoid of G. The holonomy group at a point is just then, in a very straightforward manner, the vertex group of the holonomy groupoid at X. All right, so Kirill Mackenzie showed in 1987 that the Lie algebroid of the holonomy groupoid is our gamma curvature reduction of A. So recall that A is the sum of the image of the connection, the Lie algebroid connection, with the subspace of the adjoint, the subbundle of the adjoint bundle generated by the curvature. So that is, the algebroid tangent to the holonomy is equal to the algebroid generated by curvature, or more descriptively, Lie groupoid holonomy is generated by Lie algebroid curvature. So this is the extension of the Ambrose-Singer theorem to the Lie groupoid Lie algebroid setting. When our Lie groupoid is the Atiyah groupoid of a principal bundle, this produces the classical Ambrose-Singer theorem. So this is indeed a generalization. So I won't go through all of this, but I'll mention that the idea of proof is quite nice. We show that, or Mackenzie showed that both sides of this equality are equal to the smallest Lie subalgebroid of the tangent Lie algebroid that contains the image of the image of the Lie algebroid connection. So this intermediate construction we can call the gamma holonomy algebroid of A. The first equality, and it's also interesting how each of these resulting equalities 1 and 2 are either smooth or algebraic. So 1 is essentially a smooth result. It is an immediate consequence of the relation between our path connection and our Lie algebroid connection of our notion of differentiation and integration. The second identity follows well. We can show that the gamma curvature reduction is a Lie subalgebroid of the tangent algebroid that contains the image of the connection. And then, so it exists in the class of things of which we are taking the smallest. And then we can show that if we have any Lie subalgebroid of AG that contains the connection, it must contain all linear combinations of brackets of horizontal lifts. So in particular, it must contain the curvature. Additionally, as it's preserved under the bracket, being a Lie subalgebroid, it must be stable under the application of our covariant derivative with respect to any tangent vector on M. So this shows that any Lie subalgebroid containing the image of the Lie algebroid connection must then contain the gamma curvature reduction. Well, this is a little bit of a trivial example. I mean, or it is literally the trivial example. If we apply this to the trivial U1 groupoid, connections, Lie algebroid connections are canonically are in canonical bijection with one forms on M on the base. The curvature is identified then with the exterior derivative of those one forms, and then it becomes very easy to obtain the resulting expressions for the curvature bundle, the gamma curvature reduction, and the holonomy groupoid. All right, and then more complicated examples are substantially more complicated. Okay, so that was the relatively classical setting. What Derek Krepski and I had set out to do is to try to extend this to double Lie groupoids and LA-groupoids. So what I'll do in this section is to introduce both of these newer constructions. So first, a double Lie groupoid, it is a commuting square of Lie groupoids, which, as would now be familiar, is subject to smooth and algebraic conditions. These algebraic conditions are, again, compositional conditions. We think of elements in V here as being vertical arrows. So let's say these green arrows drawn here. Elements of H, we are thinking of as horizontal arrows, so these black arrows. And then elements of S, so S is itself a space of arrows over both H and V, as being a space of double arrows or two cells, which span both the vertical and the horizontal arrows. M itself is sometimes called the base or also the double base. So a compositional condition that we would want to apply here would be that when we have four of these double arrows lined up with each other, so imagine one here, it shouldn't matter if we first compose horizontally and then vertically, or vertically and then horizontally. This is, I suppose, a bit of an extension of the idea of associativity, that order and direction of composition should not matter.
Casey, what is the initial idea or motivation for this construction?
Well, to be perfectly honest, I'm not sure physically what the
Or
motivation.
mathematically
Uh,
too. I mean, you can generalize, but in which sense? What do you try? What we are trying to describe, or you are waiting for it?
I'm not sure. I guess that is the honest answer. How they're introduced sometimes is as being it's like a Lie-groupoid in the category of Lie-groupoid. So it's like a Lie-groupoid over a Lie-groupoid.
Kind
Maybe
of. This is what I thought at the beginning, more or less, but I wasn't sure if this was the main idea, or the idea, or whatever. You know,
yeah, it's a Lie-group, or I believe it is a Lie-groupoid object in the category of Lie.
category of Lie-groupoids.
Yeah,
Yeah.
yeah.
Okay. Okay. Yeah. That sounds cool. Thank you.
Yeah. I
Yeah.
think this is a general idea in category theory, right? Like you can get higher and higher, like you have objects and morphisms, and then you consider a higher category where your morphisms are the new objects, and you have morphisms of morphisms, and so on and so forth, right?
Yes.
Yeah, I mean, it's a way of understanding it, but as here, sometimes there are other motivations, or there are people are looking for some nice properties or whatever. So that's what I was asking. Okay, thank you, Casey. For me, it's your answer is enough.
Yeah, thank you. And so as mentioned, this is one approach to higher category theory. And if we drop all of the geometry, then here we're looking at what's called a double category. And so Derek Krepski and I have found that actually double categories are some of the most tractable realizations of higher categories. The data is pretty tame when we just say, okay, it's just a category in the category of categories. All right, so so then an LA-groupoid or a Lie-algebroid groupoid is the it is the differentiation of the double Lie-groupoid, but only in one direction. So here, only vertically. It comprises a pair of vertical Lie-algebroids, so B over H and A over M, which themselves have horizontal Lie-groupoid structures. So B is a Lie-groupoid over A, H is a Lie-groupoid over M. In analogy to the comment that was earlier made, we can think of an LA-groupoid as being a Lie-algebroid on a Lie-groupoid. And then all of these maps need to be structure preserving with respect to the maps in the other orientation. Here is an attempt at a picture of what's going on with this. So this double arrow, little b, is that then lies here. So it has a source, which is an arrow here, and a target, which is a Lie-algebroid element here. Those are the horizontal maps. If we just take the vertical map, well, then we send the double arrow to the Lie-groupoid arrow above which it sits. That arrow itself has a source and a target in M. And because all of the structure maps have to commute, if we project B, this Lie-algebroid element B, down by the anchor map to H, then we get a tangent vector in the space of arrows. The image under the differential of the source and target maps of the base Lie-groupoid must then coincide with the anchors of the sources and targets of B. So there's a lot happening in these constructions, I think. We now, so we have something new. We have a construction. I'm sorry, this is not new to Derek Krepski and I, but in the setting of double Lie groupoids and LA-groupoids, there is a new construction that is of the core. The core bundle is the kernel of S, of the kernel of the source map S along the unit embedding of M in the base manifold H. This is very similar to the construction of the Lie algebroid of a Lie groupoid. Here, I think of this as being like doubly. It's as if we are applying the tangent Lie algebroid process twofold in the horizontal and the vertical direction. There's a so the target then in the Lie algebroids restricts to the core, and it gives us a map delta or partial, which is a Lie algebroid homomorphism from the core to the Lie algebroid A. This map is called this collection is called the core complex of the LA-groupoid, and it appears to play a similar role with the LA-groupoid as the Lie algebroid plays to an ordinary Lie groupoid. It's like an extension of the Lie algebroid by this extra infinitesimal 2-arrow data. It is, so I am not familiar with that many concrete examples of double Lie groupoids and LA groupoids, but there is a very easy one, and that is the double Lie groupoid. It consists of collections of 4 points on the base manifold M. The respective source and target arrows in the horizontal and vertical directions then pick out pairs of those pick out pairs of those 4 points in 2 different ways, and then each of those M2s are pair groupoids over M. The tangent LA algebroid is then the tangent algebroid over M and the tangent algebroid over M2 with the pair groupoid structures horizontally. Okay, so in this final section, I will describe some constructions that Derek Krepski and I have been thinking about, and these we have, so these are new to us, and then I will conclude with our with a higher Ambrose-Singer conjecture that we have and have been attempting to work towards. First of all, we'll define a double path connection on a double Lie groupoid to simply be a compatible pair of path connections gamma on the in the vertical direction on the Lie groupoid. So this is sending paths in M to paths in vertical arrows and paths on horizontal arrows to paths in 2 cells or double arrows. These connections should be compatible with each other in the sense that this outer diagram should commute. We add to this the data of a path curving K or uppercase kappa which will take homotopies of paths, so paths of paths in M, two tails there, to paths in the space of two arrows that span that span the assignments given by capital gamma. So formally, K should be a path connection on the pullback by the gamma holonomy of S, the space of two cells, to the space of paths on M. And the following picture should make this more clear. Gamma, the path connection, is lifting one paths, or lifting ordinary paths P and Q. K should send a homotopy that spans P and Q, or with sides P and Q, to a two cell given. So the homotopy then is that the boundary is given in dark blue here, H of S. That should be lifted by K to a two cell, a path of two cells here indicated in light blue, that from the lift of P to the lift of Q. So again, K sends homotopies in M to two cells spanning the gamma lifted paths. And then we define the holonomy groupoid with respect to gamma and K to be their images in the double groupoid. So the double groupoid of all gamma lifts and K lifts. On the infinitesimal side, we define an LA-groupoid connection gamma to simply, again, just be a compatible pair of Lie-algebroid connections, vertical Lie-algebroid connections. We'll say that the curvature of these connections is just the compatible pair of curvatures R on each of these Lie-algebroids. Then we define an LA-groupoid curving in parallel to the double Lie-groupoid curving as a lift of the gamma curvature, which is a which is a adjoint bundle valued two form by the map in the map partial in the core complex of the LA-groupoid. Our curving again is a lift of the ordinary curvature by the structure map of the core complex. The idea is that the curving and the Lie-algebroid connection together should induce or should yield a Lie-algebroid connection on the Lie-algebroid of the pullback by the gamma holonomy of the space of two cells over the space of paths. So as K assigns two cells to homotopies, or two arrows to homotopies, in M, kappa, its infinitesimal counterpart, should assign infinitesimal two cells to infinitesimal homotopies, where here an infinitesimal homotopy would be a variation of the path PT along some variational vector field X. Kappa should control a development of that infinitesimal 2 cell, which is an element of B in our LA-groupoid, vertically over this horizontal path P. The 3 curvature S of our our infinitesimal curving and connection data is just the exterior covariant derivative of the curving kappa, and then we define and then one approach that seems plausible is to define the curvature complex by analogy with the Lie-groupoid Lie algebra setting, to define the curvature complex instead of curvature bundle to be the smallest gamma stable Lie algebra subcomplex of the adjoint complex. So in the Lie algebroid setting, this is exactly what we have, except this space, these first 2 spaces, LC gamma kappa and LC, are both 0. So it should be the smallest gamma stable subcomplex that contains the image of the curvature. And so finally, we would like to have a result that establishes that higher curvature generates higher holonomy in the double Lie-groupoid and LA-groupoid setting. One plausible seeming approach is to establish that the adjoint complex of the LA-groupoid associated to the holonomy subgroupoid is the curvature complex of the LA-groupoid tangent to the original double Lie-groupoid with connective structure. In this direction, we also conjecture that the partial again is the structure map in the core complex of the LA-groupoid, that the partial vertical subspace of the curvature subcomplex is generated by the 3 curvature. So the non-vertical part should then be generated by the ordinary 1 curvature R. So this has been one thing that we've been thinking about over maybe the past 2 years or so, and it has turned out to be fairly technical, but also I think extremely interesting and fruitful. All right, thank you very much.
So thank you, Casey, for your talk. Thank you very much. Okay, is there any comment, remark, question? Well, I have a comment, several indeed, because somehow this double Lie group is something like a higher order element in a category, as like a Lie group in a category, a Lie group, we said. So in 31, what I noticed is that you are somehow lifting the objects in the first category to a second order category. So I was wondering if there is some categorical methods or idea to do this in a functorial way. I mean, there is somehow a manner in the category theory that allows you to lift objects that they are in the first order category to the higher one. Can you follow this idea somehow, or to have which are the guests you have to generalize what you have for Lie-groupoids and Lie algebroids to this double category theory, or how did you do it? What's the way of thinking of it?
Well, so my personal background is in differential geometry rather than category theory, and so that I think has been reflected in some of the direction of this work. We haven't used high power categorical tools to try to do this, but rather to work with these objects as if they're just complexes of, I mean, like systems of smooth manifolds and smooth maps between them. That is to try to stay as close to the geometry as possible. But yes, I think it would be, well, in fact, I know that results of this type have been established in much more abstract settings within higher category theory, dealing with the category with like higher categories of or like infinity categories of manifolds and stuff like that.
I haven't. Yeah, sorry. Please go on.
No. I was just going to say, yeah, but our approach has been, insofar as possible, just to treat them as like within the standard scope of differential geometry.
And I have another question. I mean, do you have present some simple examples? Do you have any other examples of the double Lie groupoids or the LA-groupoids or algebroids?
Yes, there is okay, so the example that we had tried working with explicitly is even though it is relatively quite simple, it's still extremely complex. Well, not extremely complex, but fairly complex, because you need to describe four separate groupoids. But yes, mostly like when I try to work with this concretely, it's with combinations of trivial groupoids and just unit groupoids. So groupoid where the arrows are all units. And then these connections and curving data, then if you choose it in the right way, then you can identify the connections and curvings with differential forms, and that can provide kind of a nice, very, very simple test setting to play around with some of this stuff.
Anyway, I think that these structures appear somehow in the generalizations of driftfold type doubles or something like that. Also, maybe in higher Poisson geometry they appear, because I'm not pretty sure, but I think I have seen these things in several problems. Can you comment on it? Also about homotopy or something like that. Do you remember any of these things? Maybe.
I'm not sure, but I am making a note of Drinfeld doubles so I can follow up on that. Yeah, I mean, as far as, again, just as far as its connections with other fields like physics or even things within differential geometry, I'm not super familiar with that. Yeah, it's more of so I should be, but now it's sort of, or up to this point, has been more of an exercise in trying to understand higher manifestations of curvature and holonomy.
I understand. It's been interesting, very general, and I was wondering because, as I said, I think I have seen these things in several fields and even in things I was interested in. But right now, I don't remember. The most thing, it was something about, as I said, different doubles. Indeed, a TR algebroid groupoids construction. I was doing stuff of this several years ago. Well, I don't know, really. But anyhow, thank you, because it's nice to understand the Ambrose-Singer theorem intuitively and to see how it can be generalized to more general framework. So thank you very much, Casey, for your talk. Thank you for your participation. And I hope that I will see you someday in Europe. Yeah.
Great. Yes. Thank you.
Thank you, Casey. Okay, see you around. And to the other people, let's say that our next seminar will be about, let me check, because I think that it was Ian. Once again, and I will tell you, yeah, next week, yeah, we have Yuan Bukataru, Kusa University, and he hasn't still given us the topic, but I think the I don't remember exactly now. Okay, so we will send you the information and also the recording from Casey. Thank you, Casey. And if you can send us the slides, what your notes, it will be a pleasure to publish them on our webpage.
Wonderful. I'll send that now.
Thank you, and congratulations again for your permanent position.
Thank you.
I think it will be fine. Thank you. See you, everybody, in a week.